Hello and welcome to the video. And in this video, we will see a small signal model of MOSFET. And we know that ID is a function of VGS, VDS, and VBS when there is no small signal increment. And thus the change in ID due to small signal increment is delta ID, which is a function of delta VGS, delta VDS, and delta VBS, obviously. And as the delta ID change is very small or small, the function is linear. So we can show the function in this manner where delta ID is basically dou ID by dou VGS at the operating point or the bias point times delta VGS plus dou ID by dou VDS at operating point times delta VDS, and similarly goes for VBS. So now we denote the changes by lowercase alphabets. So basically we have GM, GDS, and GMB. So basically we have ID or the small signal plus the large signal current, which is GMVGS plus GMVDS plus GMVGS plus GDS-VDS plus GMB-VBS. And thus we can draw a DC small signal model of an MOSFET. And we have our drain terminal, we have our source terminal, and we have our gate terminal. Along with that, we have our bulk terminal with body effect, VBS. And GMVGS and GMVBS are shown like this because they are controlled by voltages at gate and bulk. And GDS has its two terminals, one at drain and one at S, and total ID flows through drain to source. So this is the DC small signal model. And now when we peek into the physics of MOSFET, so there is a distributed capacitance which is formed between gate and the channel. So basically the gate and the channel which contributes in our main circuit, and also due to the depletion region over here, there will exist a capacitance between drain and body, and also source and body. So there are these kind of capacitances which we can call parasitic capacitances, which are between gate and drain, gate and source, which is between drain and body, and source and body. So CGD and CGS, basically capacitors due to gate and drain and due to gate and source, are intrinsic to the operation of the MOSFET, as we know that a MOSFET is basically a capacitor which controls charge in the inversion layer based on the gate voltage, which in turn controls the current. And the values of those intrinsic capacitances depends upon the operating point. So over here, we have two regions of operation of a MOSFET, and in triode region, we basically have a linear inversion layer, and our CGD equals to CGS equals to half of width into length of the MOSFET times the capacitance due to the oxide layer, and where WL is basically the area of gate and Cox is the capacitance per unit area of the oxide under the gate. And in saturation region, we have a pinch off at drain, CGD. So the saturation region, we have 0 volts of CGD, but 3 by 2 times the capacitance per unit area of the oxide under the gate times the area of the gate. So this is the capacitance CGS in saturation region. And along with that, due to the overlaps, we have C overlap times width, and over here also we have a little C overlap times width, and this is basically due to the fringing capacitors, and we should consider the effect due to the fringing capacitors as well. So basically this is the overlap of gate on drain and gate on source, or vice versa. So if we want to calculate COV, capacitance due to overlap, so we have the structure of our MOSFET where this is our width of the MOSFET and this is the top view. So we can easily see that the capacitance is proportionate to the width of overlap of gate and drain or gate and source, which is nothing but the width of the MOSFET. So C overlap is directly proportional to the width of the MOSFET. So basically now CSB and CDB are the junction capacitances, and we have a 3D view where this is the length of the drain, this is the width of the MOSFET, and we have a depth. So if no information is provided, we can assume LD equals to 2 times minimum length of the gate, and the depth is already fixed by the process team. So CSB and CDB are due to the overlap area at the bottom plus some parametric capacitances, and which can be given by, basically CSB can be given by the capacitance due to the area of junction times area of source terminal plus the perimeter of source terminal times capacitor due to the perimeter of junction. So similarly, CDB can also be given in that manner, and we need all the above discussed parameters while modeling a MOSFET in a simulator. So we have GDS, GM, and GMB in small signal picture, which contributes to a DC structure. And we have CGD, CGS, CSD, and CSB, which contributes towards the AC analysis of the MOSFET. So equation of ID from square law model in the saturation region is given by this equation where 1 plus lambda VDS is very small value, and as compared to 1, so basically lambda VDS as compared to 1 is nothing but 1 only, and when this 1 is multiplied, so we are left with only this part of the equation. And when we take dou ID by dou V ds, we get our GM to be the derivation, dou VGS, sorry. So from the when we do dou ID by dou VGS, we get the GM, and this is the partial differentiation with respect to VGS. So from this equation, if we consider one like this entity as 1, so our GM comes out to be this value, which is basically nothing but this value. So GM can be written in different formats, and it can be, the equation for GM can be rewritten in basically in those 3 formats, where in this format it shows the dependency of GM on VGS minus VT and ID, or in this format it shows the dependency of GM on ID, purely ID, and in this form it shows the dependency of GM only on VGS minus VT. And we will use each of these in right context, or what parameter we actually are manipulating. So based on that, we will use any one of these dependencies or equations for GM. For example, we will use this equation for GM when we will only change the parameter VGS minus VT. So it depends on the indications and trade-offs. So basically, square law model is only valid when VGS minus VT is greater than 6 times VT or 150 millivolts, where VT is thermal voltage. So when in square law model equation is valid, so our GM comes out to be this value, and in the subthreshold region, the equation of our ID changes, and thus the partial differentiation, a partial derivative with respect to VGS is nothing but ID by n times or neta times VT, where VT is the thermal voltage. So now GDS is given by this value, and basically GDS comes out to be ID times lambda, because this corresponds to ID times lambda, and GMB is nothing but dou ID by dou BBS. So when we take a partial derivative of ID with respect to VBS, we arrive to this conclusion. And as we know that VT is a function of VBS, so GMB can be given by this equation, where this corresponds to nothing but GM, and we have dou Vt by dou Vbs, and as Vbs is equals to minus Vsb, so this cancels the negative sign over here at the beginning. So we are left with GMB equals to GM times dou Vt by dou Vsb, and this dou Vt by dou Vsb can be a number of order half or 1 by 4 or even more or less. And usually we reverse bias the source to body junction, which limits the utility of GMB. So now we saw that when you make a physically identical components, they are nominally identical, and there will be existing a small mismatch between them, and that's related to the physical size of the device. So exactly same is true in case of MOSFETs as well. So let's say we have two identical MOSFETs with two identical widths and lengths. So if we bias them with given VDS, VGS, and VSB, they should get the same current, but as usual, it's not exactly same. And in case of resistor or capacitor, as we discussed earlier, to describe the minute difference there was R naught and C naught, and delta R and delta C respectively. But in case of MOSFET, there are more than one parameters. So there are more than like in case of MOSFETs, there are more than one parameter to describe the minute difference. So we'll talk about the mismatch in MOSFET, and we will use the square law equation, which is representing the saturation region, ID in saturation region. And ID is basically nothing, but this is a constant quantity which we can denote by K. So ID is nothing but K times VGS minus VT square. And now there are only two parameters, K and basically VT, for calculating the mismatch. So we will describe this mismatch in terms of K and VT. So let's say we make 10,000 parts of MOSFETs and measure the difference in K and VT for each pair and relate it to the nominal value of K and nominal value of VT. So let's talk about the VT mismatch, which is described by sigma VT, which is standard deviation in VT. So in case of VT, it is not normalized to the nominal value of VT because the nominal value of VT can be 0 or very small. So basically sigma VT will be given in many millivolts, and it's basically sigma VT1 minus VT2, and it's given by area per unit square VT divided by root of width into length. And the K mismatch can be given in percentage because it can be normalized. So sigma K is nothing but sigma K1 minus K2 by K naught, which is basically area per unit square and for K divided by root of width into length. And we will see how do we calculate the effect of mismatch, and we will discuss these parameters in great detail in the next video. Uh, for this video, I think that's all for this video.